All right, welcome everybody. Okay, so I'll go through all the stuff we've done since last time. So there were 52 PRs merged, and this number is always an underestimate because Asra merges stuff in the morning before I get up. Yeah, this is in sort of reverse chronological order. We have a Docker file for HEIR development now, so if you have been having trouble with building stuff and you want to work in a Docker file, then you can do that. We have been spending a lot of time on the new packing system using ISL. So there's a couple PRs for code gen, and then a lot of PRs for just integrating the packing system into the rest of the pipeline and doing lineage kernels and getting things working. So I'll talk more about that later. I think that will be a topic of discussion. I have also been on the side working on some test and CI runtime improvements. I haven't really cracked the case yet, but the next thing I want to do is to create a Google Cloud storage bucket to cache build artifacts. And that is supposed to be more efficient than the GitHub cache because it can cache individual build target artifacts independent of, like, you don't have to cache the whole thing as one big bucket. So you can just cache like just the LLVM MLIR build. And then reuse that across different CI actions. So if I have to deal with some internal billing stuff, but and like security stuff, but once that's done, then I think it should be much faster. There have also been some improvements to the plain text backend and the C ABI. So if you look at some of the plain text end-to-end tests, you'll see that they have a much nicer interface than they used to have. I think this is kind of opened the door for us to remove MLIR runner, which should also improve build times because we would build a significantly smaller fraction of the LLVM code base when we're doing that. Yeah, okay, so we're working on this like Torch to CKKS pipeline, and Torch, the way that Torch does activation functions in MLIR is it will create a separate function for the activation function. Which makes it difficult for us to match on it and do polynomial approximation. So we have a new pass that will inline the Torch generated activation functions. That's part of this bigger Torch lineage to CKKS pipeline, which we've been working on. We'll talk more about that later. There's an, okay, so we had this arithmetic DAG data structure that was like a simplified arithmetic circuit. We used it for polynomial approximation, and now we've decided it would be really helpful for implementing lineage kernels so that they can be tested by both having the same code generate the IR as be able to run it on test static data. So we have it set up so that you can basically say, okay, have this IR, or in this mode it will generate IR, in this mode it will run it on some test vectors and just like produce the output, and so you can have the same code do both, and you can unit test things, and it's quite nice. So we use that for our lineage kernels now and for our baby step giant step implementation. And then apologies to I forget his name, who never replied to our GitHub issues, but we need to do eval fast rotate now, like rotation hoisting. And so we went ahead and implemented it. And so now there's a new pass called OpenFSG fast rotation precompute, which will identify all of, as long as there are more than one rotation of a ciphertext, it will call the fast precompute function from OpenFHE, and then it will take the result of that and thread it through like the fast rotate, eval fast rotate function calls. The reason this is specific to OpenFHE is because Latigo has a very different API for it. So I think it's going to be hard to figure out what to share exactly. Okay, in progress PRs. Some of these were merged this morning. We've been working on pre-packing plain texts. Because we have like some machine learning examples where the thing that takes the longest is Clang compiling the resulting OpenFHE code, because there's so many plain texts that are hard-coded in the function body. And so we have a new pass called split preprocessing that will identify all of the plain texts that it can precompute. It will hoist them to, it will basically split the function into like the normal function signature, which will eagerly pack everything and then call a preprocessed function. And the preprocessed function will take as argument prepacked ciphertexts or prepacked plain texts. And then there's a separate PR that's in works that will create helper functions to do the packing for the plain texts alone. So that where API will be able to say like encrypt arg0, prepack arg2, etc., and then pass all of those in. So that will require like changes to the Python front end and all that as well. This propagate attributes during inline. So for polynomial approximation on torch generated activation functions, we need to know the domain and range, or the interval of approximation to use for these. The idea is that we will attach these at the very beginning of the pipeline before it actually goes through MLI or through HEIR. And so the func call is going to be annotated with the domain lower and domain upper and the degree of approximation. And we want to make sure that those are propagated to the inlining step. So that's what this PR does. There's a old, the context is we have a vibe coding tech debt week at Google right now. So we picked a bunch of random tech debt issues to try to vibe code to fix. And so this one is the Python front end. We're having name conflicts when you have a @compile decorator on two functions in different, like two functions that are in different Python scopes. So they shouldn't override each other, but then when you compile them, then they do override each other in the HEIR backend. So this fixes that by giving them unique names. There was a big change to remove MLIR runner in favor of lowering to LVM. So that was for the mod arith functional tests and the polynomial to LLVM functional tests, or polynomial to arith, or polynomial to mod arith, I think is the lowering from polynomial to LLVM. So now these are just lowering all the way to LLVM and running them directly instead of using MLIR runner. After this, there's one more use that we need to delete that I think is not relevant anymore, and then our builds will be faster. We have this lower polynomial eval methods. This was another just like cleanup. The Patterson-Stockmeyer Chebyshev used this arithmetic DAG. That was like our first use case, but all of the other lowering methods don't use that yet. So this PR is to refactor those to use the arithmetic DAG. And then there's another one where, again, the Patterson-Stockmeyer lowering will drop small coefficients, anything less than like 1e minus 12 or something. And so we want to have this in all of our lowering methods. Then there was some progress on the lowering of key switch of CKKS relinearize. And so, I think me and Alex and Eric have been working on this, and there's still some decisions to make, but basically it's doing like the implementation of part of this key switch interop. There's also now in layout optimization, I added an analysis that can look backwards in the IR to see like, okay, is this layout that is being hoisted, is it, if you keep looking backwards, is it eventually going to be free? Like, is it eventually going to be folded into something else, like an assigned layout or a function argument? And so that's like a pretty simple layout or pretty simple analysis, but it makes the layout optimization much smarter about its like heuristic cost analysis. Power. Okay, that was there's an AI port. I think this was Alex's port of Raghev's OpenFHE BinFHE backend. That's in progress. And then, the current polynomial approximation pipeline still doesn't use the Chebyshev polynomials approximation. It converts it back to the monomial basis. And so there's a few minor cleanup things to actually get it to stay in the Chebyshev basis so that we can use the Patterson-Stockmeyer Chebyshev lowering. Okay, new issues. We now have OpenFHE version 1.4, which comes with functional bootstrapping and CKKS. I don't have time to look into that, but if someone wants to try an ambitious project, there could be some research involved in figuring out how to actually use functional bootstrapping in CKS in the compiler in a systematic way. We are, yeah, okay, this is the helper functions for client-side plain text packing. So yeah, I think the implementation on that has started, but I don't think a PR has been pushed yet. So I would recommend no one else work on that. Okay, oh, sorry, this is circuit bootstrapping. Yeah, okay, so we had, I was consolidating a couple of different issues where we talked about circuit bootstrapping into one, like, okay, here's like how should circuit bootstrapping be supported in HEIR? Okay, and then also I sort of consolidated a bunch of issues around CKS parameter selection. I remembered that we have this sim FHE thing, and I think I saw a paper where they were using sim FHE in a loop to decide on parameters. And so I thought maybe you could do the same thing in HEIR. So we added this rotate and reduce op as like a first party op in TensorX, so that we could like share its lowering across all the different passes that we're using it now. And so then there's an opportunity to canonicalize rotate and reduce. There's an issue opened about an Onyx to MLAR converter. I think there are some issues with it, but I don't know where we landed on it. We can talk about it next. This is the issue for lowering CKS relinearize. Oh, this is fun. Jean-Philippe of Latigo created a new Rust library called Pulpy, as in the octopus. And it's using it's not using RNS representation. It's using a different representation, which is supposed to be more efficient. And so it's in Rust and could be fun to support in our library. I have no idea. I don't know much about it, but could be interesting. Then there's an issue about we have this baby step, giant step lowering. And we made some assumptions about like how to pick the baby step and giant step sizes. There's a couple of people discussing different methods to navigate that trade-off. I don't think we figured out what exactly to do that's best. Okay, so that was the notable new issues. I'd be happy to open the floor for discussion, but I wanted to mention the HEIR paper that was rejected from CCS is now a preprint on arXiv. So we're aiming to resubmit in January to, I think, Usenix, right? They have their second round. That's February 7th or something. So yeah, I think we'll probably be discussing that more offline in the next few months. But yeah, okay, so maybe just a quick update on the layout system. So it's been very smooth sailing as Oscar and I have been like chugging away at it. Now we can get MNIST to compile through the system. Like obviously there are some of these caveats, like it's not using the Chebyshev lowering for the polynomial approximation, and we don't have the bounds on the domain, like the lower and upper bounds on the domain, automatically persisted there. But if you hard code some of those things, then it works. So we have some cleanup to do, but it's been very nice. Oh, look at that, Asra, nice. We have the OpenFHE C++ code, cool. Okay,
yeah,
and
so
then
this just in case anyone does want to compile it or anything, it should work. It takes about 8 seconds, and there's a checked-in traced model.pt in that commit that has the PyTorch model that it was trained it was generated from. And so the weights are pulled in from that traced model. So you're going to see, like, in the main file of that, you're also going to see some, like, torch, grab, like, load model, and then load all the weights into it, and then pass those weights into the FHE function. So you're going to see like a torch dependency in it.
And so part of that 8 seconds is also that we are like eagerly packing the plain texts during the evaluation. Yeah. So we can expect that. And I think we haven't done the hoisting of the rotations, have we? Or is that in there?
No, that includes everything. I regenerated this like yesterday. So that includes eval fast rotate in there, and then it also includes baby step, giant step.
Cool. Right on.
But it was also on my machine, and it's questionable whether or not it was parallelized.
Like whether OpenMP was run? Yeah, okay. We can do some more work. But yeah, like basically we just got it working a couple days ago, and we're cleaning up the rough edges. But yeah, so Now you'll notice that the layout is using this like ISL formatted string, which is like very nice because we can like name things, like we can name the variables. It used to be like D0 through D9 or whatever, and now we can say like, this is the ciphertext dimension, this is the slot dimension, this is the row and column dimension of a matrix, and then everything else would be like local variables that would have like a little existential quantifier in front of them. So it should be clear where things are coming from. And we have this like interop layer where you can go back and forth between the ISL representation and the Pressburger MLAR representation like losslessly. So we like if you have some functionality in ISL that you need, you can always go there to get it. Yeah, the implementations of like passes like convert to ciphertext semantics are significantly simpler. Although right now I think it's still, we have like it's supporting both, so we need to like go ahead and like delete all of the old code. Oscar wants a sanity check on.
Yeah, could you like present that tab for, okay, this is something for like after, actually. We should open up the floor if anyone else wants to talk. I guess this is going to take 2 seconds, never mind. Okay, so this is just because I need to get this out of my head, but so the HEIR approximation works on the unit interval, right? But if we have a upper lower bound domain that's larger than that, then we have to scale down to that -1 to 1 domain. So if you see that line 122 to 127, if it's like the variable func here is the thing that we're approximating. And so we need the HEIR approximation to work on the unit interval. And what I see on 124 is that, like, don't we need to take our X value, which might be in like minus, it might be in like lower to upper, and scale that down to -1 to 1, and then apply the function, and then scale it up.
So I think what was happening in the original one was that it was pre-composing. So you start with a value that is in A to B. The first thing, like, so like this composition down here is doing the composition that takes A to B, shrinks it down to -1, 1, and then you apply the approximation that is defined on -1, 1.
Wait, but then why?
But the function values should be the normal ones from the non-compressed interval, right?
Okay, Jeremy, I guess that resolves what 136 is saying, but I thought, I guess I didn't realize, I thought 131 had to be what Alex is saying. The input func scaled needed to be working on -1 to 1, right?
Yes, I think so.
So func scaled, though, if you look at the definition of func scaled on line 123, that X is being blown up into the larger interval.
Yes, but that's the right way around, right? Because like you have to call the func on the original like ladder range, right?
Like, yes, right. Okay, yeah. So input, right. Okay.
So here, this X that's given here needs to be -1, 1. It's scaled up and then called in the func. Okay.
Cool. My test was failing, and I knew it was on this, and I knew it was whether or not we needed to pre-compose or compose. But thanks. I just needed to get that out of my head today.
Right on. Yeah. Okay. I get the last thing about the layout system is that like what we're doing next is we're going to move on to the convolution kernel so we can do some CNNs, and just like focus on the other performance issues that we know about. Yeah. Okay. And then my task is to like figure out how to automate this like intermediate value range estimates for the polynomial approximation. Okay. So that's any questions, concerns, or topics to discuss?
I guess like just for the MNIST and everything like that, and if you want to stress test this or something and you have a torch model, we can only support fully connected layers. So like only expect this to work with mapmuls. And then again, that's why the next step is convolutions. So if you want to stress test it, feel free. It should deal, like you won't have to do any like manual zero padding to get power of 2 matrices. Like that's all handled by the layout system now.
Yeah, it would be nice if we could like get some people to figure out like approximations for other activation functions. Like there's like gelu and celu and on all these things that like I don't even know their definitions and how we would match on them, or like what torch produces when it does that.
So torch, when you create torch to MLAR, it'll JIT it with through XLA. So it's going to give you arithmetic ops like we have in that ReLU.
Right, it'll give you arithmetic ops, but I don't know which particular arithmetic ops it will give you for something like a gelu or a celu that we would have to match on in the polynomial approximation pass. So that's like my question is like what patterns do we need to add there for which activation functions? And then like for people who want to do Onyx, right? Like Onyx will probably do something different, right? And we'll have to figure out like what Onyx outputs look like, so we can, you know.
Yeah, I think TinyBert would be amazing. Like next step, or just a linear layer.
The only tricky thing on that end is that when you're doing the cybertext matrix multiplications, you have to split by an extra dimension based off of the attention heads. So that might not be something that's clearly implemented yet if you're just implementing matrix multiplication kernels, because you'll have a third dimension that you basically need to match. Yeah.
We also don't have a matmul kernel. We have a matvec kernel, but we don't have the map matrix multiplication kernel. So that's something that we would need to add. And like I know there's multiple of those, and one's in the coefficient domain, and there's like some complexity there. But like I think what I wanted to try Lawrence's tricyclic matrix multiplication kernel, right? That seemed pretty cool. And I looked at the definition. It also seemed relatively easy. So like it was like simple to define at least. So I would love to try that out when we have some time.
Yeah, I think now that we have like the layout handling and hopefully soon have actual matmul, I really want to go back to the Python front end and do intrinsics for matmul, because I think one of the reasons why I stopped working on that was because I had some progress on having the intrinsic, but then nothing happened because we didn't have a lowering file, right? But I think we're now at a point where if we chuck some random NumPy arrays through the front end, HEIR will actually not choke up on like most of them, right?
So yeah, we have a lot of support for different tensor ops now through the layout system. So I feel like there's a lot we could do there.
So I think obviously the work with Eric on the lowering to LLVM I think has a bit high priority, but maybe once we have that kind of wrapped up, the next step for me would be to look at the Python front end and make it like tensor capable properly. I think there's also recently I think the Cutlass folks over at NVIDIA have a Qt DSL in Python that goes to MLA as well, and I think that might be a more principled way to do a Python frontend than sort of our Frankensteinian thing we do to number. So I also want to look into that because, I feel like those people probably know how to lower a tensor to MLAR, right? But I don't know what the licensing situation around like that is. I know NVIDIA's licensing stuff can be a bit difficult to work with.
Who were those folks over at NVIDIA, Alex?
So this is, I don't know, I don't remember the names of the teams, but this is part of the Cutlass library, which is their linear algebra something library. And it's a Qt is the name of the DSL. So Qt DSL in Python, and I think it's a kernel specification language, more correctly.
Awesome.
Yeah, so the reason I saw this is because it's going to be presented in next month at the LLVM developer meeting. So hopefully there'll be a chance to ask some questions.
I'm so sad I can't go.
Talking about things you're sad about not being able to go, let me take this moment to advertise the event happening next week in Cambridge. I think nobody here on the call is from the UK, but maybe somebody's watching this, on the recording later, who knows. So next week there'll be happening this MLAR school hosted by Tobias Grosser's group and a few other people at Cambridge. Obviously, if if this is your first time hearing about it, it's probably too late to register. But if you are in the Cambridge area on Friday next week, there will be an open compiler social called the Open Friday at the top there with some interesting talks and presentations. For those who've been to the HACS, the Higher Assurance Crypto Systems workshop, we took a lot of inspiration from the way that event is run. We actually got one of the co-organizers, Alan Gunn, to help us organize this, at least tutor us a bit throughout the process. So I'm really excited for this event. It's also where all my free time has been going this week. But yeah, I will be leading a expert theme on crypto and MLAR. But just based on the attendee list, I think that's going to be very heavily slanted towards ZK rather than FHE, because there's half a dozen Ethereum foundations that people are going to show up. So I'll try and get some HEIR stuff happening there, but realistically, the excitement is probably going to be on the ZK front. But those were the same people that Jeremy and I already talked to a tiny bit at the HACS thing, or various events around that, who are also really interested in having better upstream support for arithmetic style things, constant propagation and folding and constant CSV for
Moderith. Yeah.
For weird things like Moderith, specifically not just for our Moderith, but for arith-like dialects that they might have downstream. And so I think that's definitely something that I'll try to bring up next week as a potential hackathon project.
Upstreaming Moderith?
Well, not necessarily, but more figuring out what kind of traits, interfaces, whatever we need to introduce upstream, and how we need to make the existing propagation passes generic enough to figure out how to work with just interfaces. Which I think, I don't know, Jeremy, I think you had thoughts on this as well. So if you
I mean, I have had pushback from the upstream MLAR maintainers on doing this at all.
Yes.
So I don't think we're going to get anything. I mean, a lot of the pushback has been on parsing and printing. They're we can't do parsing and printing in a way that's that generic. Maybe they would feel differently if we did something some passes that could be upstream. But I also kind of feel is there really anything stopping us from having a generalized Moderith that is upstream that works for everybody? I feel maybe that's one thing that you could suss out at that among the ZK folks is okay, you guys might only have hard-coded some particular prime or whatever in your thing, but if there was a Moderith dialect upstream with all of the stuff that you'd expect from it, would you use that instead? And probably they would say it would be in pain to migrate, I guess. But
I mean, even if it turns out that we do need slightly different dialect, maybe messing with the upstream stuff that already exists, maybe what we do is we just have a side-by-side coexisting pass set that lives upstream that works on interfaces that we can all implement, right? Because I remember you got a lot of really, I would say, irrational pushback on some of the proposals, right? So yeah, we'll see.
Yeah.
Maybe.
But I feel like they would not be opposed to having a new dialect. They would just be opposed to changing, changing parsers and printers in a way that is not aware of out of tree stuff. So if there was a Moderith dialect in tree, I think they would change their minds and say, oh, well, this is something that you can see is in tree and is presumably used by people. So it's okay to have a special hard-coded path just for Moderith in this parser or whatever. So I feel that could be a alternative. And I'm being considered a maintainer now at this point. So I've been.
Did you sign up for one of the things? One of the new hierarchy positions that they...
No, I didn't sign up for a position, but I'm reviewing a lot of code, and I'm reviewing all of the... I'm basically maintaining or helping maintain the dialect conversion framework now.
So Matthias will be there next week in Cambridge, right? So
yeah. Oh yeah, I'm sure.
That'll be really fun. So yeah. So for those who don't know, he's the guy who rewrote the dialect conversion framework. So. So I mean, we'll also have a bunch of maintainers locked in a room, so maybe we can, convince them in person to reconsider their views. But yeah, I think that's probably the most relevant thing for HEIR that might happen next week is mod arith related things and building better tooling upstream for sort of crypto style arith. I don't know if there's anything else that we would want to push from our side for HEIR. I feel now that Jeremy is so involved upstream, whenever we run into something that we need upstream, Jeremy just does it, right?
Well, it would be very helpful if we had one other person from HEIR with commit access, because if Asra creates the PR, then I can review it and I can press the merge button. But if I create the PR upstream, then I have to get somebody else to review it and then I can merge it. But if we had Alex or Asra with upstream commit access, then that would be
I've been dragging my feet on actually upstreaming things to LLVM because primarily because prior to the switch to GitHub, it was just such a pain. But now they've been on GitHub for ages now, and I just don't have an excuse anymore. So I'll make sure to start contributing upstream as part of next week, and then hopefully if I keep that up, will get me committer status.
The other thing you could do if you were interested is start upstreaming some of the ISL stuff to FPL. Like there's like a bunch of low hanging fruit there.
That's a really good point. I'll see. I'm not sure if the students that did the FPL work are going to be around next week, but if they are,
yeah. I mean, Tobias, I was talking to him a lot about this while he was schooling me on ISL, and like basically it's like the easiest place to start is the simplification routine. It's like 14 subroutines. Each one is doing like one simplification technique, and like 4 of them are in FPL, and the other 10 are still waiting to be streamed. And so it's like a very easy piecewise, like or piecemeal process. So like, and I'd be happy to review those, right? And I'm sure I'd learn something.
There is going to be also like there's going to be some SMT-ish folks, some formal methods folks that might also care about like this kind of stuff, not just the crypto folks. So yeah, I think that's a really great idea for like hackathon projects for next week. Also, I think the mod F3 like general.
For people who are confused by the acronyms, ISL is the integer set language. That's the like polyhedral analysis library that was written in C that inspired a lot of the upstream work in like GCC and LLVM and also MLIR. FPL is, I think it's called Fast Pressburger library, and it's the Pressburger arithmetic is like the underlying math of integer polyhedrons. And so that's the name of the library in MLIR. And that was what we were using originally when we were trying to do the layout system. And, we decided we needed more intelligence from ISL because some of it hadn't been upstreamed to MLIR yet. But okay, Seda has been typing stuff in the chat, and I want to give her a chance to chat, to talk out loud.
Sorry.
Hey, hi everyone. So it was for the discussion back in around, I guess, 10 minutes ago. You were discussing the TinyBird implementation, also the need to support the matrix multiplications and multi-head attention blocks. I just wanted to give my 2 cents that they all are actually just a linear transform following the JKLS work. And most of the implementations, like for the LLMs and the encrypted LLMs in the literature, like you probably know there are groups from Chugang University, Seoul National. They mostly follow the same JKLS blueprint, obviously with different optimizations. But once you have a solid implementation of your linear transform, it's actually easier to move forward to the others. They're just some variants of the similar linear transform.
Yeah, that's a great point, I think JKLS is definitely a baseline we should want, even if maybe eventually it will be sort of like, not selected for in the vast majority of settings. Because like a lot of the work still use it. I think increasingly people are using different approaches, right? But yeah, I think that would be a really good idea. It's what everybody compares against as well, I think, in the like MatMul paper space, right?
I think it's, sorry.
Go ahead.
Yeah, it's like there are newer methods for like matrix multiplications, but I feel like it's governing the LLM part of the literature now.
I also like there's a mention in the abstract of this paper that they allow to pack multiple matrices into one ciphertext if they're small. And I feel like that's an area that we have like not even yet attempted to tackle yet.
Actually, like in general too, like we haven't really tackled multi-tensor packing into one ciphertext, which our layout will support.
I think it will make sense if you have like like if you'd have to take all of your data that you'd like to pack and put it into one tensor. But then the layout system would support it.
Yeah, right, because it would just be like row 1, column 1, row 2, column 2, and then it'd be, you know, 0. That we'd only have, you know, the first
Right,
two dimensions going into one part and the second 2 dimensions going into the other part.
we could even do this as like a non-FHE specific, just tensor level transformation, right? Where we take a bunch of tensors, pack them together, and then we lay it. Okay, cool.
Yeah.
That seems like one of these things that somebody should have written already, but it's probably harder to find it and port it than it is to write it, which is like the tragedy of MLAR sometimes.
Yeah. Yeah, and it'd
you
also
think
be
there-
really nice for the like bootstrapping. Like Halo does this too, of saving on bootstrapping multiple ciphertexts by just packing them into one if they're small.
Yes.
If your layout system supports compaction from Felipe, that's exactly what they do. But it's essentially like you have to have the same type of gap slots inside of your ciphertext. So if they all have the same runs, then what you can do is just rotate and then add them together. And then it would cost one additional level to decompact it afterwards.
You know, one thing that we haven't really had like found a need for, to be honest, is striding the layout yet. Like we haven't really, I guess maybe we haven't gotten like weird enough
Yeah.
to have gaps.
Well, the compaction thing, that was something that I didn't quite like. It seemed they had in Felipe, they had these like implementations of higher level things in terms of lower level tensor primitives, and some of their implementations would introduce striding, and then they would say, okay, if we introduce striding, then we can apply compaction in order to fix that. But like we haven't yet found places where like the operations that we would naturally do introduce striding at all. And so I
Right.
haven't found like a direct need for compaction yet. And so I was still kind of unclear to me to what extent this was like a trick introduced by them where they could like, they like introduced striding specifically like in like a slightly unnatural way so that they could do compaction, and that like together that helps overall, or if there was something else going on.
To my understanding here, their layout system was fairly simple. So they only support basically row, column, and tiled layouts. So they don't have a concept of like diagonalization or base set giant step. A lot of the summation dimensions, so if you're doing like matrix multiplication and then you need to sum along a dimension, happens along their slot dimensions. So if you move the summation dimensions to the vector dimensions, your resulting layout wouldn't have any striding. But if the summation dimensions are along the slot dimensions, then you'd have the striding. So that's kind of like where that striding came from at least what I saw.
I see. It's like because we like default to diagonalization, like we are kind of preserving the like no stride.
Exactly. Yeah.
Yeah.
Okay.
But even more general,
Right.
whenever we like rotate and reduce, right? We technically get a bunch of slots that we don't need anymore.
We get repetition, yeah. And so I feel like
We-
there's probably something we could do where we could say, okay, if you need to bootstrap a bunch of different ciphertexts and they're all repeated in a bunch of ways, then what you could do is combine them together, using up the extra slots, and then split them apart later.
One thing that I want to do like future project is like our ISL representation like should give us a like view on what slots are being used in the result. And that way we can actually do like a slot analysis of like the used data, and then identify where we have like places where we can like squash things together. But the nice thing actually about the ISL layouts is right now, instead of like we don't, so for example, in like in the matrix multiplication diagonalization case, where we might have like the input repeated if it's an n by m matrix, we have the input, which is, so n by m, the input is repeated every m. Then in theory, the result could be laid out in a way that's repeated every n, but actually what we do is that the result layout only has 0 to n as like live hot data. So it doesn't hold on to the fact that it was repeated. So it would just say that, oh, the rest of it is like open slots. Like we don't care, it doesn't matter. So we also like don't really have, I guess, like a slot analysis tool to tell us like what parts of it were repeated, because that might also be useful later, in terms of like, oh, we don't have to rotate something.
Yeah, I think another thing that's incredibly useful is to know which slots are 0 or 1, like statically, because those are like the ones that make it easy to combine things, right? So yeah, I think maybe we just I guess like when we come up to situations where we need those, will probably be the point when we get them. But yeah, I guess these are also maybe the things that make like that sort of start being more FHE compiler specific rather than like just and then vastly underselling Alvarez and Jeremy's incredible amount of work, just implementing like existing packing techniques from the FHE literature, or just again underselling like 10 years of MLIR work being normal tensor things, right? Like with a view to like the next iteration of the paper, maybe, right? Like putting in all this like slightly FHE specific stuff makes it a bit easier to justify why this isn't like just a tensor X thing.
Mm-hmm.
For like previous layout systems, at least most of them that I've seen have some notion of like a repeated dimension or a gap dimension, and usually those are the two that you need in order to just define what values are repeated or where the zeros are.
Yeah, I think we probably don't need to write the gap, or like we don't need to write that to the IR, but it would be nice if we had an analysis that went through and held on to that information internally. So then it kind of is like, it doesn't matter if it's holding what data structure it's holding on to.
Yeah, I mean, I think there's also like a slight nuance in that, like in some places the repetition matters. Like it's actually something that's used because it will rotate and then use, like when it rotates, it uses something from one of the repeated pieces versus if that was like zeroed out, it couldn't actually do that rotation and have it make sense. And so I feel like there's some, there's an aspect to which we could say, okay, this is repeated data, but it's not actually used by anything. So it's free for an optimization to reuse it.
I think there's not even anything upstream that will do like constant folding or like elements of a tensor, right? So like, I think any of the analyses upstream mostly treat tensors as like entire things, right?
What do you mean by constant folding elements?
Like, for example, like if we, like there is obviously scenarios where we know something is 1 or 0 because like by definition, we just wrote it into that, right? But if we want to track that kind of thing, for example, like after you multiply with a like one hot vector, right, a bunch of elements are now 0, those kind of informations. I don't think anything upstream like can do that for tensors, right? Where like not the entire tensor is constant time known, but like
you're saying just like no analysis upstream that can.
I don't think I don't think they do that, right? Like I don't think that's a thing that exists.
I thought int range analysis worked on tensors, but it might not. Because that maybe on an int range analysis that will say, okay, this is, and like for us, it would just be like, oh, did you multiply this by 0? And then if you multiply it by 0, you know that.
Which doesn't really work for the thing, but for that one, I might actually do because it's simple enough, right? Yeah. Yeah, I don't know. I thought you were talking about like actually doing the constant folding, and the thing that they don't like upstream is that if you constant fold a bunch of tensors, then you will end up littering your IR full of basically like dense constants that take up a lot of space. And so they're like, okay, we don't want to do that. So we kind of do want to do that. So I feel like it might be worthwhile for us to add some like constant folding materials, like materialize the canonicalized tensors. I'll actually add that to the list for next week because I feel like this is one of these like most normal programming things don't want that. But yeah, CodeGen for like tensor constant folding, right?
Because, like, or something where it's like, I think where we could have some like tuning of it, where we could say like, oh, if the tensor is bigger than 10 values or something, or 100 values, then you would want a constant fold. Or then maybe if it's too big, you don't want to constant fold it. If it's not,
or like if the fraction of constant values is too low, it's not worth it. Those kind of things, right? Yeah,
like that. Yeah. But yeah, okay, this is great. Now that the packing system is like in a good place, we can start doing some interesting things with it.
Can we, with the packing system, I guess we can also now represent the like non-packed coefficient style map more, right?
Yeah, we could.
Because
there's nothing about the packing system that knows that like is specific to whether it's an NTT form or coefficient form.
Right.
Yeah, because I'm just thinking that like that might be the absolute easiest matmul kernel to write because it's just literally lineage.matmul.
I think Alex isn't saying like coefficient packing versus slot packing. He's just saying like let's just do a naive matrix multiplication.
Well, I guess my point is if we can express the transition between those two phases, right? Then we can use the like, you know, plain text.
Right. I think
matmul.
he's talking about like Gentry's and the Crypto Lab matrix multiplication kernel, which is in the coefficient domain. And so like that one, it is just whatever 4 plain text matrix multiplications,
Yes.
but it needs to know about the structure of the ciphertext is the problem, right?
Yeah.
Like it needs to know the fact that the ciphertext is 2 components and has this particular structure. So I don't know if we'd be able to express that at the tensor X level. But like the idea of saying that, okay, there are some kernels that only work. I think that we have this for like like multiplication versus convolution, right? Like if you do a convolution in the coefficient domain, you get if you do a multiplication, I forget which. If you do a multiplication in the coefficient domain, you get a convolution of the, and sometimes you actually want to do that, like if you're doing convolutional neural networks, like so. So I think there's some point at which we need to have like a some encoding in the some concept in the lineage kernel system that knows about coefficient domain versus entity domain, and like has like a cost, incorporates in its cost model the cost of switching. Yeah, but I don't know exactly what that's going to look like. I think once we implement one of these, like probably it will be the matmul kernel, then we'll have to like actually think about this hard. Good evening, Valder. Welcome. Thanks for joining in. Is there any topics you want to announce?
No, what I got a little question, and maybe if you have some spare time for it, is that for now, well, the next steps that I want to do is represent the high level functions in basically at that TensorFlow PyTorch level. So at really at the beginning, I would like to express like a ReLU function, a one-hot function, like all these types of stuff. But I was just wondering what would the appropriate dialect be to be placed in. Because you want also to keep them alive at all of the levels as well, like in every dialect.
I mean, so well, like at the high level, we match on some activation functions for polynomial approximation, and there we do stuff like, okay, if you see an arith.max and one of the operands is a constant 0, then you can call that thing a ReLU, even though, and so we're planning on doing this for all of the other activation functions that we care about, but we don't have like proper ops for them. And I don't know if there's like a place for that.
I was gonna say, like, isn't there an upstream dialect that has these? I would assume that like TOSA, stable HLO, one of them, something has that.
Well, stable HLO isn't upstream. And
right.
TOSA's kind of a mess. So there's also like, yeah, I think that there's like, it's like a valid question of like, where could these ops live?
Or could we maybe do something more abstract, like an affine mapping on a tensor, and then just define what kind of the mapping you want? And just with
I mean, we could have like we could like some of them make sense to add, I think, to the math dialect upstream. Some of them probably it makes more sense to have like a math ext dialect in HEIR, which I wouldn't be opposed to. I'd thought about doing this before, but like I'm wondering if there's going to be a point at which we like actually take a dependency on something like stable HLO, and then we'd have all those ops there. So yeah, I don't have a good answer for you.
Yeah, I think the problem with that is, right, that then we would have like the diamond dependency issue with like MLIR.
With LLVM,
so,
yeah.
Yeah. If that wasn't the issue, I think it would be super obvious to bring in stable HLO, right? But it just seems like a nightmare from the actual like dependency management point of view. And we
Yeah,
just
I mean, another option is we could have a fork of the like relevant stable HLO dialect, and just like vendor that in tree, and then we would have it probably be stable because like that dialect wouldn't change very quickly. But I don't know which stable HLO dialect. There's only one stable HLO dialect, right? And it's the stable HLO dialect. So I don't know if it'd be easy for us to like take a subset of that we need.
And also that's only for the more official function that you want to use in the neural networks. Once you go to the more of exotic feature extraction functions, that actually we want to target because that's the most interesting applications for now. Yeah, then you're also kind of limited to also stable HLO doesn't support it.
Yeah, I mean, I think it'd be fair to create just like a math-xed dialect in HEIR, and like we could use that to store like intrinsics that we don't have ops for that come from the front end, right? We can use it to store, fancy things that you use in whatever Löwenstein or whatever, like fun things that you have going on there. So I think I'd be, unless there's any objections from other people in the room.
Well, as I see, the MATX dialect is already there, but it's only for now supporting a sign function. Yes.
Oh, but I think that's.
Oh, I did that.
Yeah.
But I think you actually upstreamed that one by now, didn't you?
No, I was going to upstream it to math, and I think I got some support for it, and then I just never got around to it. I think there was some questions about like what do you do with floats, like what's the float semantics of? Do I still have my PR open?
Lay on anything that's to assume that like semantics are a thing.
Yeah, like
But
we
no,
don't really worry too much about IEEE float semantics, but
no, I was more looking like math having like the whole math there, like having semantics is a kind of funny concept, but I guess that's where they want to go. But yeah, that's a good point. We actually have that dialect already. I mean, for that one, it was supposed to be temporary, right? Because it's for the sign op, SIGN op. But yeah, I think we should just use that. I think we had and have a lot of success with TensorX, right? That's working out really well for us. So I think MathX is not an issue.
yeah, this was.
I also see Ed just posted a bit on functional bootstrapping and OpenFHE in the chat.
Yeah, I was trying to play with it. For the most part, I've only got it to work with like 8-bit inputs and outputs. So the value ranges are constrained from like -127 to 127. And I kind of wanted to see if this was like actually feasible to like use for like LLMs and other machine learning models. I think for smaller models, there exists a lot of 8-bit quantized models, so that should be perfectly fine. For LLMs, I did like a very naive thing where I had like a plain text version of it, and I scaled all the nonlinear functions, so Geely and softmax, to be 8-bit, and we saw about a 4% drop in accuracy. However, I think there do exist like 8-bit BERT models, so I'm going to try that next. I'm curious to see how the performance would increase, because the benefit of functional bootstrapping here is you would save a lot of levels, not having to do a really deep polynomial approximation. I think there's also techniques to also combine and amortize the conversion cost of the slot to coefficient domain, and then doing a coefficient matrix multiplication, and then doing functional bootstrapping. So those are kind of like next steps for me for my research.
Yeah, I also recently saw a paper that I think fused ReLU into the bootstrap or something. I forgot what exactly that was called, but if you type in fusing ReLU bootstrap, you should probably find that. And yeah, it seems like that is kind of like where the like LLM world is now heading, is doing clever combinations of like integrating stuff into the bootstrapping algorithm.
Oh, but that's like being done in TRHE for like since the beginning of TRHE, and even like the scaling down of your 8-bit back to 8-bit, or like your 12-bit down to 8-bit is also done in the ReLU as well, and the table lookup. Sorry.
Right, but I guess I don't know if that's the same thing, because this is, I think what they realize is that basically like all the like heavy workload that like the modulo approximation is doing in a CKKS bootstrap, like you can coerce that into computing other fun nonlinearities is like that paper. So yeah, I think yeah, I mean that's we're very far away from being able to implement any of those in here, but it's also nice to know what's going on, like the state of the art LLM space.
Yeah, this is definitely something that I want to poke at a little bit. So, I'll give periodic updates on this.
All right, we're at time. Any last comments? All right, I'm gonna stop the recording, and then people can keep going as long as they like.